All right, welcome to ISAT430. This is lecture 2, physical properties of materials, GD&T, and measurements. All right, so this lecture is composed of two parts. The first one is physical properties of materials. So basically, we're gonna introduce the rest part of the materials from the prior lecture, and then we're gonna talk about some dimension services and their measurements. Well, we discussed about the mechanical properties of the materials. Now let's look at some physical properties of materials. While the physical properties are also very important to the application of these materials because those properties can be used in different industrial applications to achieve certain functions. Let's look at what are the physical properties. So one is volumetric, so which means when the material is exposed to certain temperatures or certain other external conditions or environment, the volume will change. Another one is the thermal property, and also electrical property like conductivity and electrochemical properties. Also, some components in the products must do more than withstand mechanical stresses, because in a lot of cases that people use their physical properties like conductivity or heat transfer or transmit light, those kind of properties to design different products. All right. So the reason it can be used a lot in manufacturing is because, for example, in machining, several properties of work materials can determine the cutting temperatures, and it will affect the tool life. And we are learning all these physical properties because we want to know, okay, if I'm using certain material, what cutting temperature should I choose, and I know how much tool life it is, for that kind of material, and also some of the physical properties can be manipulated by different conditions. For example, silicon, right? Can use its chemical or physical processes to change its properties so that it can be used in semiconductor industry. All right, now let's look at the first relationship, which is volumetric and melting properties, and these kind of properties include some density, thermal expansion, and also melting point. First, the density. So density is a measure of mass per volume. You all understand this, but I want to point out there's another concept, which is specific gravity. So specific gravity means it's a density of the material relative to density of water. So basically, it is using the water as a reference. So compared to water, if it is heavy or it is not heavy for different materials. So this is a specific gravity. And you can see from this this table and find out the different densities for different materials. And some of the phenomena you can notice is that normally metals are heavier than polymers, right? Heavier than polymers, and also mostly they're heavier than the ceramics and the silicon as well. While comparing the ceramics and polymers, ceramics are heavier than polymers. So this is density. And if you look at the coefficient of thermal, so which means thermal expansion, you can also see how different materials can how the volume of the material will react to the temperature, and look at those values. You can notice that polymers usually they have larger values, which means they are more sensitive. The volume is more sensitive to the temperature. So that's why in a lot of times we use injection molding. To make different parts by melting those kind of polymers with very, relatively lower temperature compared to metals and ceramics. You can see those melting point for polymers are 260 Celsius, to 115 degrees Celsius. But for metals and ceramics, usually they are much higher. Sometimes even have to be, over 1,000 or over 2,000 Celsius. So this is a thermal expansion. So thermal expansion is a measure of how much material expands as a function of temperature. And it has been used in manufacturing a lot because the part can be heated to increase size and cool to decrease size to permit insertion into another part. So this has been used in assembly a lot, right? Used in assembly. First, you can cool a part, and then you can because cooling the part will decrease the size, and then you can insert it into a certain another part, and then you can increase the temperature, and then to let it make it bigger. So that's how you do those kind of assemblies. And also heat treatment is another major application when we use thermal expansion. So when materials are, especially the metals, when they are going through some heat treatments, usually the temperature will increase and then cool it down in a different speed of changing the temperature. And then with that kind of speed of changing temperature, their structures or crystalline structures will also be modified to different physical properties, mechanical properties. Same as welding. In welding, we use melting point in order to decide what kind of metals can be used to weld, and what kind of serving materials should be used. So melting temperature means it's a temperature at which it transforms from solid to liquid state. And if you reverse this process, and the same temperature it's called a freezing point. So it means when it was in a liquid state and you cool it down, and there's a temperature that it will return to solid. So that's a freezing point. Another concept, the heat of fusion, means it's a heat energy required at the melting temperature to accomplish transformation from solid to liquid. You can see for different materials the behaviors of thermal expansion. And we compare the glass and metal, and a lot of times we can make some alloys as well. So if you use some alloys, so some solid alloy will be located in the middle, so it will not be the same as metal, that there is a straight or sudden change of its structure. But it's not as low as glass, so it's resides in the middle. So we mentioned about this, that the melting temperature has been used a lot in manufacturing because of those kind of manufacturing processes, which we will be discussing in the future lectures, like metal castings, right? And if some material will have some lower melting temperature, then it can be used a lot in casting. Right? For example, zinc, right? Steel, steel actually has higher melting temperature, but it's so widely used. Plastic molding the same. The plastic bottles, a lot of different plastic parts, they're all made of plastic molding. Sintering of powder metals. So one application is actually 3D printing. For metal 3D printing, the raw material is the metal powder. So you are using different technologies, for example, laser to melt those metal powders, and then the metal powders will create a bonding between them, so you can create different parts. All right, so that's something that about physical property of the materials. Now, next we're gonna move to the GD&T and the measurement. So this is the more about design, product design, and also engineering drawings. From this graph, you can see there are a lot of dimensions, arrows, and also control frames. So mainly, we're going to talk about the control frames. Those kind of control frames are specifying the features. The features of certain, either a plane or a surface or a line or axes or different positions, many different features of a part. So if you are working in a manufacturing environment, you need to know how to read those kind of drawings, how to read those control frames. What do they mean? All right, so a little bit background about GD&T. So GD&T is a means of dimensioning and tolerancing a drawing, which can consider the function of the part and how this part functions with relative parts. GD&T is a system that uses standard symbols to indicate tolerances that are based on the features geometry, and it has been used a lot in last 15 years because of ISO standard. Also, it's been specified in the ANSI standards as well. All right, so these are some of the commonly used geometric characters and symbols in GD&T. We're going to go through each one of them and see how they are used in engineering drawings. They include flatness, straightness, circularity, cylindricity, line profile, surface profile, perpendicularity and angularity, parallelism, circular runout, total runout, concentricity, position, and symmetric and symmetry. All right. First, let's look at the difference between tolerance and allowance. Okay, so allowance means it's some intentional gap that is designed by the designer. For example, in this shaft and hole. All right, so allowance means, okay, with the smallest, right, with the smallest hole and the largest shaft, what is the gap, right? What is the gap? So means allowance in the smallest hole means it's 1.250, right? Because the tolerance for this hole is 1.250 to 1.251. All right, now we have smallest hole minus the largest shaft. Right, largest shaft. So in this case, they all go to two extremes, and then we can find out, okay, what is that gap? What's the difference? So this is you want to see the difference is 0.02. This is called allowance. Right? This is called allowance. Well, another concept is a clearance. So the maximum clearance means it's largest hole. The difference between largest hole and the smallest shaft, right? Smallest shaft. So largest hole is 1.251, and the smallest shaft will be 1.247. So in this case, we get the maximum clearance is 0.04. So we I purposely designed this shaft and hole to have a Lorentz of 0.02 because we do not want them to, have some kind of collision, right? Have some collision or really touch each other, and also we do not want it too big. One of the the gaps too big, so we might lose its position. So that's why we need to define the Lorentz and the clearance. All right. A common symbol we'll see in the future is this M symbol. So the M symbol, capital M with a circle, it means maximum material condition. So maximum material condition means we want to design this kind of feature or size of the part with the maximum amount of materials, right? For example, this part. All right, it's a block. It's a solid block with a hole in it. If we are talking about maximum material condition, it means that we want the block material as much as possible, and the hole as small as possible, right? So in this case, we can have the maximum material condition. Well, let's look at another example. Let's call it A. Now this is B. Look at the B part. B part is a solid block with a pin on it. Well, now we are talking about what? We are talking about this pin, and if we want maximum material condition, means this pin has to be we want this pin has as much material as possible, right? So if you put this M symbol in it, means the pin's diameter should be as big as possible, right? Of course, it has to be within this tolerance. So this is what it means by M. Well, after we learn about M, we know the L. So L means the least material condition. With the same example for A in this case, right? Because we want the least material condition means we want the hole as big as possible, and we want the pin as small as possible for B. Next concept is datum. So distant datum means it's a theoretical exact plane or axis and a point location that GD&T or dimensional tolerance are referenced to. So basically, it's a reference. It can be anything. It can be a plane or axis or certain point. And this is a typical symbol for datum. All right, so look at this example, the left part, right? See this? It is talking about the top, right? The top plane, right? The top plane, right? This top plane is the datum we're looking at, right? Datum we're looking at. This is the top plane. You can look at it as surface or whole plane. Well, if we are saying that this control frame is to control the feature of what? The feature of maybe it's a cylinder, or it's a shaft, or but it is a round. It's a round or a round shape feature, right? Because of what? Because it's a diameter. Right? This is called a control frame. So this diameter does not mean that this diameter 0.2 does not mean does not mean that this dimension is 0.2, because this 0.2 is the tolerance. It's only talking about tolerance, right? It's not talking about what is specific diameter of it. It's the tolerance has to be within 0.2 tolerance, and the left part is talking about what is the relationship. So relationship for this will be, okay, this cylinder or this shaft should be perpendicular to datum A. If the datum A is what? Is this top plane, and this cylinder or this shaft should be perpendicular to this one. And to what extent? To 0.2 diameter tolerance. So this is what it's talking about. And so now you know how to use datum in the control frame. All right, when I'm talking about control frame, a lot of times actually is a lot more complex than the simple one. So this is the one control frame, and the left part, a typical control frame, is composed of three major parts. The first one is a geometric characteristic. You can see this is a position, right? A symbol. So means it is to it is talking about where is this, a diameter thing. Either it is a hole, or it's a shaft, or it's some cylinder or something else. Where is that located? So this is a geometric characteristic. Well, next is the middle part. So the middle part is talking about what is control you want to have, right? What is a control you want to have? Well, the first is always with a symbol. So the symbol is the tolerance zone shape. Now it's a diameter, so now you know what is it's a hole or it's a shaft, right? And the next one is the tolerance zone size. So it's 0.25. The next one is material modifier. So you do not necessarily have all of those composing in it, but you should have at least the tolerance zone shape and also the tolerance zone size. Sometimes you can add this material modifier, right? Maximum material condition or least material condition. Well, the last part of the control frame is the datum reference. And sometimes you have one datum, while sometimes you might have more datum references, right? For example, in this part, the hole or the shaft it has a location that is referenced of three different planes, right? It can be planes or it can be different points. All right, how to read this control frame? So the text with underlying lines are fixed. So you can always say, hey, the position, right? So position, which is a geometric characteristic, the position of the feature must be within or what? Within a 0.25 diameter tolerance zone at what? At the material modifier, at maximum material condition. And then relative to all these datums A, B, and C. So this is how you interpret a feature control frame. All right, now let's look at all the symbols. First, it's a position symbol. You can see this is a typical position symbol. And so it is talking about where is this hole, or where is feature located. Usually it has to have different datums. For example, this is datum A, this is datum B. So which means this location has to have a reference to this two planes, and also it has a tolerance zone of 0.03. Sometimes I'm going to say, all right, there's a tolerance of 0.05. How is that related to 0.03? Which one should I use? Well, it's not a conflict because the diameter tolerance is 0.05. Right? It can be in a different positions, but it also need to be at the position because of this feature control frame, saying that it has to be in the position that is relative to A and B with the tolerance of 0.03. So in this case, we are using 0.03 for this hole. All right, next is angularity. So angularity describes a specific orientation of one feature to another at a referenced angle. So this is how you look at the angularity. So do not get confused with the tolerance of angle. Right? It's not talking about angle. So angularity here is talking about the whole plane, because you can see this plane has what? This plane has variations, right? This plane has variations. So that's why we're talking about this kind of variation should be within a certain tolerance, which is 0.03 in this case, right? It's not about angles. Angles will have to say, for example, it's 45 degree, plus minus 5 degree. So this is about tolerance of the angles. But if we are talking about the angularity, means what is the variation of this kind of plane. And this is the control frame. How you use that in engineering drawings? Make sure you have a datum, right? In this case, it's the datum A. It's relative to datum A. This is how it formed the angle. All right, next is circularity. So circularity means, it describes how close an object should be to a true circle, right? Mainly it's talking about the cross section. It's more about a plane, right? A cross section plane. It should be a circle, and so the symbol is simply a circle, and you can also describe what is the tolerance zone. It's 0.05 in this case. Next one is cylindricity. We're gonna put the cylindricity with circle, next to each other, because cylindricity not only describes circularity but also is talking about straightness. Right? If you look at a circle as circularity as a 2-dimension, well, cylindricity will be a 3-dimension, because it also have this kind of a straightness, and so the symbol will be a little bit different. It has a circle, then will also need to have 2 lines at 2 ends, right? Parallel lines at 2 ends. So this is how you describe cylindricity. And when you use the control frame here, this is how you reference that. Next one is parallelism. So parallelism means is tolerance that controls the parallelism between 2 surface or features. Parallel symbol is this one, and of course, because it has to be parallel, you need to have a reference. Which plane do you want it to be parallel to? Sometimes it can be a plane. Sometimes it can be other features. Okay. Now this is for this surface. This plane should be parallel to this plane, right? At 0.03 tolerance zone. Next one is concentricity. So it is to establish a tolerance zone for median points of a cylindrical or a spherical feature on the part. So meaning, how do they concentrate, right? Comparing of the two circles, like a shaft, right? The outside diameter is different, right? So this is how you specify the feature of concentricity in this part, right? So this is referencing the feature itself, while A is referencing what? Referencing the axis, right? The axis, because the 2 parts has to be concentrated to the axis. Well, the next one is profile. So the profile does not have to be a really strict line or a flat surface. It can also be a certain change shape of a profile, non-linear profile. All right. So the symbol for this is this one. And also, you need to make sure it's a reference to different datums, right? A and B here. So this is a profile symbol. Well, next one is perpendicularity, and we talked about perpendicularity before. We use the same example. Well, another example is the axis, right? So if it is axis perpendicularity, now you can see the second graph to the right, and so this control frame means that the hole, right? The hole is perpendicular to what? To datum, the datum A. Datum A is probably it's the one end of this part, right? One end surface of the or plane of this part. So it means it needs to be perpendicular. So this is the hole, and this is the plane of A. This is the hole, right? So it's perpendicular. And 0.03 means right, it has a tolerance zone of 0.03 for this hole in this feature. Well, next, runout. So runout is talking about how much one given reference feature or features vary with respect to another datum when a part is rotated 360 around a datum axis. What does it mean? It means that, okay, for example, if you have one either a cylinder or a shaft, right? If you rotate it 360 degrees, right? 360 degrees, and how much it will vary, related to the datum, right? For example, in this case, the datum is A, right, which is the outer surface, right? Outer surface of the part. Now, if we rotate the part, right? If we rotate the part, which is the inner part here, and how much it will vary, you can see this red shape. It's not a strict circle. Right? Because when it rotates, it actually changes, right? Because variations or something else matters. So the runout is to symbolize how much it actually varies when they rotate to a 360 around a datum axis. Well, the datum axis, the A, is this one, right? Well, next, total runout. So total runout, it controls both the amount of variation of the surface as the part is rotated, but also the amount of variation in the axial dimension. Right, both the radial and also axial variation are measured. Right, so here we can see this total runout is talking about the datum A. So it's the outer surface of this part, and also is talking about the axis as well. So this is the whole axis. It has to be straight, right? Straight one. So this is called total runout. It's the same as circularity and cylindricity. Right? This is more about 3 dimensions. Next one is the profile of a line. This is similar to the profile, just as a line. It's not a plane, right? It's not a surface. So this is how you define that. Well, another one is the straightness. So surface straightness is tolerance that controls the form of a line somewhere on the surface or a feature. Well, also we can specify an axis straightness. So then it's talking about the tolerance that controls how much a curve is allowed in a part's axis, right? Well, for this control frame, you can see that it's talking about, okay, this feature has a diameter of 10 with the tolerance of 0.05, and it has maximum material condition. Now it depends on, is it a hole or is it a shaft, right? If it's a hole, means we want the hole as small as possible. If it is a shaft, meaning we want the shaft as big as possible. This is the axis straightness. We use the line to symbol it. Next one is the symmetry. So symmetry means we want to make sure the part feature is actually symmetric to a certain datum. Here you can see now A is referring to the top plane and also the bottom plane, and the features controlling is this part, right? You want to make sure it's parallel to the two surface, to the two planes. Also, next one is the flatness. So flatness means how flat a surface is, regardless of any other datums or features. Because the surface, also have roughness variations, planes. All right. Next, let's look at some measurements. What are the equipments or devices that are used for measuring those kind of dimensions or geometries? And first, let's look at two concepts. One is accuracy, the other precision. So accuracy means how the degree to which a measured value agrees with the true value of the quantity of the interest. So which means, say, if the part is at the, say, diameter of 2, right? At 2. Now if I measure something, I found, the diameter 4. This is far off, right? This is far off to the true diameter. But if I measure as diameter as 3, now it's closer. So comparing to 4, 3, this measure is actually have higher accuracy than the 4 one, right? So this is talking about accuracy, which is how off to the actual true value of the measure. Well, precision is different. Precision means the degree of the repeatability in the measuring process, right? All right, same. If we want to measure this hole, and I might measure it many times, and sometimes I might have really big difference. I mean, first time I measured at 4, next time I measured at 3, then next time I measured at maybe 1. Well, this now you can see have the three differences of diameter. Well, if I measured it as, say, 2.001, 2.002, 1.999, well, in this case we're talking about saying, hey, this measurement has a better precision than this measurement. So this is talking about accuracy versus precision. All right, now let's look at some different measurement instrument. So some of you already have used some of those. For example, the calipers is very simple to use, and micrometers. Of course, micrometers usually measuring some small dimensions. A lot of cases, but it has a higher accuracy to measure. And also, there's a dial indicator. So dial indicator is to measure the runout. Remember, for the runout, it's talking about if the part is rotated 360 degrees, how close it is to a circle, right? So this is how you measure runout. Now this is to fix the part, and then just let it rotate, and you have a indicator, and this is the contact, and then when it rotates, it will indicate some of the values because it will touch the contact to show it. All right. Next is a go and no go gauge. I think there's a video in this link. You can click this link and watch the video and see how the gauges are used. So gauge is also is very simple one. So go gauge means so the part can actually let it can insert it. While no go means it cannot let it insert it. So gauge has been used a lot in assembly or checking the dimensions if the dimensions are within a certain range. Because if it's too big, means it cannot get into the gauge. But if it's too small, means it also cannot go through the gauge as well. So that's why the gauge can be used as certain measurement devices to check the dimension qualities. So this is a measurement of angles. It's a bevel protractor, and so this has been used to measure some of the angles. You can watch this video on how to use it. So last, we'll discuss a little bit about surfaces. So surface has been used, quality of surface has been used a lot in manufacturing because not only because of aesthetic reasons, but also because some of the functionality, right? If it is surface is too rough, they're probably gonna cause some collisions or frictions to cause lose some energy, something like that. So that's why when we are doing manufacturing work, we also want to take care of the surface. Now let's look at what are the surface. How do you define a surface? Usually the surface texture includes 4 components. One is the roughness. So the roughness, you can look at this figure. So basically these are some up and downs at a very small scale. So this is the roughness. It's not a very flat plane. All right. Next one is the waveness. So waveness means talking about some larger scale up and downs of this. You can see this shape, right? This shape for this part. So this is the waveness. This is the waveness, and roughness is within this kind of waveness, and also lays. So lays, you can see this lay direction, lays. And sometimes you also can see some flaws. Flaws means some of the defects, right? It can be a crater or it can be a crack. Those kind of these are the 4 components of surface texture. All right, how do we measure the surface? If you want to say it has good surface, surface finishes, it looks nice. Well, sometimes we can tell from our eyes. Well, sometimes if you have a really strict surface finish, then we'll probably have to use some devices to look at it. Some devices, 2. One is contact, the other is non-contact. For a stylus instrument is the contact one. So it has composed of stylus and also the head. So what happens is this stylus will move, across the surface, and then because the stylus is contacting the material, so it gonna start to read up and downs to measure the roughness. Well, another way is to use a camera, right? Use a camera. We're gonna have some of the light, and then by calculating the distance of the light traveling, you can find out what is up and downs, right, of a surface. It's the optical instrument. All right. So this table shows that for different manufacturing processes, usually the surface finish will vary, and see most of the machining processes have quite good tolerances or surface finish. You can see it's plus minus 0.05 millimeters or 0.002 inches, but some of the castings is not a little bit rough. Well, as you can tell, right? If it is come out from a CNC machine or from grinding, you can see it's the surface finish looks really nicer, but it's a casting getting really rough. All right, so on this table you can see some abrasive processes have really good good tolerances for surface finish. So that's why this process has been used a lot in creating the outside surface of the part, especially after some other process, for example, sand casting or the machining, right? And sand casting, you can see it is 1.3 millimeters. Well, for machinings, it can be, these are usually at the 0.05 or 0.08. So what happens is, first we'll do first pass of the of either machining or some other process like casting, and then after we got a general shape, then we'll do some surface finish treatment, right? Either we machine it again with a different tool, or we can have some abrasive process like grinding processes. There are also some other non-traditional processes you can create surface finish. For example, chemical machining, electron beam cutting, or electro grinding or electric discharge. All these kind of processes can create a surface finish as well, but those are traditionally for electrical components or for very tiny or macro devices. All right, so there are some of the questions related to this lecture, and usually these are actually the most important parts for our knowledge points for this lecture. Make sure you can go through them and know how to answer these. All right, that's all for this lecture.